All right, here's another example, a type of calculation that you're going to need to be able to do. What is the pH of a buffer made from 0.5 molar acetic acid, CH3COOH, and 0.5 molar acetate, CH3COO minus. The pKa of this buffer, of this acid, is 4.74. And that actually is a problem that we did on the worksheet. So we'll look back, we won't resolve this, we'll look back at the worksheet. And then we're gonna continue. What is the pH of that same buffer after adding 0.01 moles of solid sodium hydroxide? I left something out. The volume of the buffer. We'll just fit that in right there. 500 milliliters. What is the pH of 500 milliliters of a buffer made from 0.5 molar acetic acid and acetate? And then what is the pH after adding sodium hydroxide? So when we're just doing the first part of the problem, we're calculating the pH of a buffer. We are going to just use the Henderson-Hasselbalch equation. pH equals pKa plus the log of the base concentration over the acid concentration. And like I said, we already did the math on this. I'm not going to redo the math on this. The pKa is 4.74. And the concentration of the base and the acid are both 0.5. And when we did this problem on the worksheet, and it's just 4.74. That's the pH. So that's the first part of the problem. Now we're going to calculate the pH after we've added this sodium hydroxide solid. And in order to do this calculation, we need to think about what is the sodium hydroxide, the NaOH, going to do with the buffer? What is it going to react with? What part of the buffer is it going to react with? How is it going to change the concentrations of the CH3COOH and the CH3COO minus? How is it going to affect, in the Henderson-Hasselbalch, how is it going to affect the base concentration and the acid concentration? Now, I did tell you that the buffer's job is to resist changes in pH, but that doesn't mean that it won't change in pH. It just is resisting it. It's trying to do everything that it can to minimize the pH change. So we can't just say, oh, this is a trick question. The pH is going to be 4.74, no change. That's not true, not necessarily true. So what we have to do, the first thing that we have to do is figure out, what does the NaOH react with? What does NaOH react with? And in order for you to know this, to be able to answer this question, you have to recognize that NaOH is a source of hydroxide, OH minus, and that is a strong base, which means that it reacts with the buffer's acid. So we are going to write a reaction. We need to write a chemical reaction that is showing how the base, OH minus, is going to react with the buffer's acid. So that means our next job is to figure out which part of the buffer is the acid. What is the acid? Now, in the last video, I told you the acid is going to be the thing that has the most hydrogen. So we're going to look back up at the components of the buffer. The one that has the most hydrogen atoms is CH3COOH. So there's the answer to that question, CH3COOH, that is our acid. So now, step 3, what we're going to do is write a chemical reaction. Write a reaction between the thing that we're adding, which is OH minus, and the buffer's acid, CH3COOH. We're going to write this out as a chemical equation. CH3COOH plus the hydroxide OH minus. This is going to be an acid-base reaction. We said the hydroxide is a base, which means that it is an acceptor, an H plus acceptor. So the hydrogen from the acid is going to move itself on over to the OH minus, and we're going to get CH3COO minus and water. So that's the reaction that is going to occur. That is what the NaOH is going to do with the buffer. It's going to decrease concentration of the acid, and it is going to produce concentration of CH3COO minus, and it's also going to produce a little bit of water at the same time. So what we need to know now is, to what extent is it going to change the concentrations of these substances? And the only way that we can figure that out, unfortunately, is with an ice table. So that's going to be our step 4, make an ice table. Where can I put, I'm just going to put it here. So we're going to make an ice table. For that reaction that we just came up with, CH3COOH and OH minus, making CH3COO minus and H2O, just like that. Now, you've done a lot of ice tables in your life, so you're feeling like an expert. You might be starting to fill this thing out already. Hold on, though. We can't jump straight into this ice table. When we're doing ice tables in problems like this where we're manipulating buffers, the ice table needs to be done in moles, not in molarity. So the initial values that we come up with, we cannot use, if we go all the way back to the problem, we can't use 0.5 molar and 0.5 molar as our initial concentrations of these things in the ice table, because the ice table needs to be done in moles, not in molarity. And the reason for that is, in this type of problem, because we are adding hydroxide, we are adding a substance to the solution, that is causing the volume of this solution to change. When the volume changes, the molarity changes as well. So the molarity is not staying the same. It is changing. The only thing that's staying constant is the moles. So we have to use moles to do this ice table. So that is going to be kind of our step 4.5. We are going to calculate the initial moles of everything. This is a very tedious problem. So we're just going to start with the CH3COOH. And let's go back up and see what we know about CH3COOH. We know it's 0.5 molar, and we know that we have 500 milliliters of it. So it is 0.5 molar CH3COOH, which means that we have 0.5 moles per liter, and 500 milliliters is 0.5 liters. So we have 0.25 moles initially of the acid. Now let's do the OH minus. Let's see what we know about that. Scroll back up to the problem. The problem tells us, this is in moles, thank goodness. So the problem tells us 0.01 moles of NaOH. So that is 0.01 moles right there. So that's not hard. And then now we're going to do the acetate, CH3COO minus. So let's figure that one out. The acetate, it tells us that we have 0.5 molar and we have 500 milliliters of the acetate, which is exactly the same as what we have for the acetic acid. I'm going to write it out anyways. 0.5 molar CH3COO minus, which is 0.5 moles per liter. And yes, we are using the volume, the same volume for both of these because they are both in that volume. They're mixed together in the same container, so they both have the exact same volume. So that's not a mistake, and it's not a weird thing associated with this problem. It's going to be the case with all your buffer problems. And like normal, we're always ignoring water in all of these equations. So we've got our ice table set up. Now we have our change. How much is going to react? In this situation, for our change situation here, we're just looking for the limiting reactant. What is the thing of our reactants? Which one do we have the least of? We have the smallest of the hydroxide, and it is all going to react completely. We're going to get rid of all of it. Because the stoichiometry is 1 to 1 to 1, the amount of change is going to be the same for all of these substances. Just like when we're doing this with X, we call it minus X plus X plus X. Same thing, the number is the same. So once we determine that X is 0.01, we're plugging that into everything in here. And then down here at the end, we can actually calculate how much we have at the end just by doing the subtraction or the addition. So when this is all over, we're going to have 0.24 moles of acetic acid. We're going to have no hydroxide. We are going to have 0.26 moles of acetate. So that's a little bit different ice problem. It is a little bit trickier, but we're doing good. So now we're going to continue on. Remember, our goal is that we want to calculate the pH of this solution. That's what we're trying to figure out. So let's move on to step 6. Step 6, what we would like to be able to do is plug the concentrations from the ice table into the Henderson-Hasselbalch equation, plug the concentration of the base and the concentration of the acid from the ice table into Henderson-Hasselbalch. The ice table is not giving us concentrations, though. It's giving us molarities, so we're going to have to recalculate the concentrations. So that's going to be like our step 6.5. Calculate. We have to actually calculate the concentration of the base and the concentration of the acid. So for CH3COOH, we're going to start with this guy right here. We have, we're going to do the molarity of CH3COOH. It is going to be the moles of CH3COOH divided by the volume in liters. Our moles from the ice table are 0.24. And we got to think about what's the volume at this point of this solution. Let's go back and read the problem. In the problem, it said we have 500 milliliters of the buffer, and we added solid NaOH. So that probably didn't have any change, didn't make any change to the volume of this solution. So we can probably assume that the volume is still 500 milliliters. In a different type of problem, it might have told you that you were adding another solution, the volume might be changing. Maybe we'll see some of those types of problems on ALEKS. But for this one, our volume is going to stay the same. It's going to stay 0.5 liters. And so we can calculate that molarity. 0.48. And now we need to calculate the molarity of our base, CH3COO minus. It is the moles of our base, CH3COO minus, over the liters of our solution. Our base from the ICE table, the moles of our base is 0.26. We already talked about how the volume is 0.5 liters. 0.26 divided by 0.5 gives us a molarity of 0.52. And okay, now we're ready to plug in to the Henderson-Hasselbalch. Okay, now go to Henderson-Hasselbalch for reals. Now we're actually ready for it. pH equals pKa plus the log of the concentration of the base over the concentration of the acid. We have to start by finding the pKa. Let's go back to the problem and let's see if we were given the pKa or maybe we were given the Ka. It gave us the pKa, so the pKa is 4.74, so we can plug that in. 4.74 plus the log of the concentration of our base, which is 0.52, over the concentration of our acid, which is 0.48. This is such a long problem. These problems take so long. And now we're going to do the math and see what we get. We get a pH of 4.77. That is the pH of our buffer after we added quite a bit of sodium hydroxide to it. The original pH was 4.74, so it did go up a little bit, but only a teeny tiny bit.